Hello, ladies and gentlemen, and welcome to section 2.2 Basic Differentiation Rules and Rates of Change. Please put these notes on page 21 in your interactive journal. And here we go. Ladies and gentlemen, we've already talked about this secant line problem. And basically, if you take a function, okay, some f of x, and you have a line that goes through 2 points in that function, to find the slope of that, you simply take f of x plus delta x minus f of x, okay, those are the y values, subtract them, and then find the difference of the x values and subtract those. This quotient right here will give you the slope, the rise over the run. You've been doing this since Algebra 1. But what I suggested before we started doing limits was if I take that red dot and move it really, really close to that green dot, we'd actually have a tangent line eventually. It would only touch at one point. And in order to do that, we have to let delta x go to 0. So the limit of delta x approaches 0 of this secant line slope. In this case, it's f of x plus delta x minus f of x over delta x. Well, when we did that, we found the slope of this tangent line here. Let me show you an example that we did in class, and feel free to copy this down on page 21. Now, this next example you already have copied down, but if you want to see it done again, just pay attention. Remember to rewind, pause, or do whatever you need to do while you're taking notes. So here's the example. Let's say f of x equals x squared. Then the slope of the tangent line is going to equal the limit as delta x approaches 0 of x plus delta x squared, because that's what the function does, it squares it, minus x squared, the original function, all of this over delta x. Now, if you were to plug in 0, we would get 0 over 0, which, of course, you just found out you can't have. So, what we're going to do now is I'm going to multiply out the top part. So I'm going to have the limit, and I know I'm going to run out of space. I don't even know I'm writing it here, but, that's how I roll. It's going to be x squared plus 2x delta x. Yeah, I should have stopped. Sorry about that. Let me just erase this. It's going to be the limit as delta x approaches 0 of x squared plus 2x delta x plus delta x squared minus x squared. So I just use Windows FOIL or whatever you do to multiply out binomials. And then I have delta x on the bottom. Turns out that x squared and x squared cancel each other out. And I'm going to do something else. Let me write the limit as delta x approaches 0. In this term right here, I have a delta x. In here, I have a delta x squared. So they have a delta x in common. I am going to factor out a delta x. And then I'm going to be left with 2x plus delta x. Kind of the reverse distributive property, because if I multiplied this here, I would get 2x delta x. If I multiply delta x times delta x, I'd get delta x squared. All of that is going to be over in delta x. Some of you all may notice, oh look, your delta x's are going to go away. And that helps us because now we can't get 0 over 0. So we're going to have the limit as delta x approaches 0 of 2x plus delta x. And if delta x goes to 0 here, ladies and gentlemen, we have the slope of the tangent line, which is 2x. That means at any point on this parabola, and matter of fact, I'm going to draw this parabola real quick right here. At any point on this parabola, I could find the slope at any one of these points here. So why would I want to do that? Well, later on, we'll be talking about the rates of change of things, like how fast something's going, how fast something is cooling, or maybe, how many people are coming in and out of the building, the rate of change of all those things. The derivative helps us find this. And derivative is another way of saying differentiation. Okay, so I'll be using those words interchangeably. Taking the derivative, doing the differentiation, those are the same thing. The slope of these lines are found by doing this slope of the tangent. But if we had to do this limit for every single problem, I guarantee you it would be really difficult and really long problems. There are shortcuts, and that's what I'm going to teach you today. The basic rules for differentiation or taking a derivative. All right, so here are our basic rules, ladies and gentlemen. We have rule number one, which is called the constant rule. The constant rule, I'm going to write constant rule. This constant rule is anytime we take the derivative with respect to x of any number. Okay, so I'm going to actually do this symbol right here, d over dx. Okay, that is the way we say it is we're taking the derivative of c. C is just a number. If we take the derivative of any number, doesn't matter which number it is, positive or negative, the answer is always 0. Now, some of you might be going, well, why? Because if you have a constant, that is a horizontal line. And horizontal lines, ladies and gentlemen, always have a slope of 0. Rule number two. Rule number two is called just what I'm going to call the linear rule. Now, this isn't in the book, but I like to show the linear rule because for whatever reasons, students make this so difficult. The derivative, ladies and gentlemen, with respect to x of x is always going to be 1. X is just a straight line that goes through the origin. The slope of that line is always 1, so the derivative or the differentiation is always 1. Okay. All right. The third rule, and probably the most used rule that you're going to be using in calculus all year long, is called the power rule. The power rule. The power rule, ladies and gentlemen, is whenever we take the derivative with respect to x of x to any power. So it could be to the power of 7, negative 12, 1/4, 0.5, any decimal, any fraction, any number. If you have x raised to any number, ladies and gentlemen, this is simply going to be that power, n, times x to the n minus 1. Some of y'all figured this out when we were doing the tangent line problem with x cubed, x to the 4th, and stuff. So it was really good that y'all saw that early. But now I'm giving you the rule officially, and now this is the only rule you ever use. This is the rule you'll use from now on. You don't have to do the limit thing, which you could thank me for later. All right. Let's go ahead and go to rule number 4. Now, rule number 4, ladies and gentlemen, I'm going to combine two rules together. So rule number 4, and I'm going to call it IV. IV is 4 in Roman numerals. Is called the sum and difference. The sum and difference rule. The sum and difference rule, ladies and gentlemen, is basically this. If I take the derivative with respect to x of a function plus or minus another function, this is simply going to be the sum or difference of the derivatives. So if I have x squared plus x cubed, then it's just going to be the derivative of x squared plus or minus the derivative of x cubed. And I should have put a plus or minus here. Instead of showing you two different rules, I'm just going to combine them in one rule. Plus or minus, if it's a plus or minus, it's going to be a plus or minus for the derivative as well. That won't change. Okay? And then we have what we call the constant multiplier rule, the scalar multiplier rule. I'll just call it the scalar rule. And the scalar rule is, it's kind of silly, but I'm still going to give it to y'all. It's the derivative with respect to x of some number times a function. Okay? If you have a number times a function, no matter what that function is, if you take the derivative of this, ladies and gentlemen, you're going to get that c times the derivative of that function. So a number times a function will, if you take the derivative or you do the differentiation, it's just going to be that number times the derivative of that function. I know it's a silly rule, but that's one of the rules they give us. All right? Okay, now, I'm going to throw in a special rule, and I'm going to explain it later, but I just need you to memorize the following rule. Rule number 6. Rule number 6, ladies and gentlemen, and it's done by VI, is called the square root rule. And I write it like a square root rule. Now, this is an unofficial rule, but I see that it helps my students whenever they're taking derivatives. For instance, if I ever take the derivative, or if you ever take the derivative of the square root of x. Now, this only works for the square root of x, and that's why I like to show it to students. The derivative of this, and we'll figure out why later, is 1 over 2 square root of x. Once again, the derivative of square root of x is going to be 1 over 2 square root of x. That's just the rule. Memorize it, know it, internalize it. Okay? Now, rule 7. Rule 7 is trig derivatives. And in trig derivatives, I'm actually going to give you 3 derivatives today, and I'm going to give you the rest of them in the next chapter. But there's 2 here. If I take the derivative of this function with respect to x, so I'm going to do sine of x first, and then I'm going to take the derivative of the cosine of x. I know some of you go, oh no, you do derivatives with trig? Yeah, unfortunately we do. Alright. The derivative of sine, ladies and gentlemen, is going to be cosine of x. Okay? Guess what the derivative of cosine is? If you said negative sine of x, you're right. If you just said cosine of x, sine of x, you were wrong. Yeah, the derivative of cosine is going to be negative sine. You know what? I'm not going to give you the 3rd rule. I'm going to wait to give you the other 4 in the next chapter. All right, ladies and gentlemen. Be honest with you. That's pretty much all the rules you're going to need for this section. So what I'd like to do with you right now is I'd like to just do a couple of examples. And these all come out of the chapter that we're working on. The next problem is actually problem number 3 from this book. So I'm going to put number 3. Oops, sorry. Put my pen back on. Ugh. All right, so number 3 from the book. It says y equals 8. Well, that's a constant. So the derivative, and I like to write it this is my favorite way of writing. I'm going to talk to y'all about different ways of writing the derivative. But the derivative of y with respect to x, that's what this means. Well, I'm going to take the derivative of this. The derivative of 8 is just 0. Yay. Number 5. Number 5 says y is equal to x to the 6th. Okay? If I take the derivative of y with respect to x, remember we always do the same thing to both sides. The derivative of x x to the sixth is 6 times x to the fifth power. Once again, the exponent goes to the front of x, multiplied times it, and subtract 1 from that exponent. That's the power rule. Okay, and then I'm going to do problem number 17. And I'm going to use some other different notation real quick. This notation that I gave you is called Leibniz notation. Leibniz was a person that's kind of the founder of calculus, the dy dx. You don't say dy over dx, you say dy dx. No over, okay? It's just dy dx. That's Leibniz's way of writing derivatives. And then there was Sir Isaac Newton, who wrote derivatives a certain way too. He had a different way of writing derivatives. So let's write this one. X squared minus 2x plus 4. Well, here we go, ladies and gentlemen. Y prime, this is Leibniz notation. This is a Newtonian notation. And that is, we're taking the derivative of y, or we're differentiating the y. This is going to be 2x minus 2 plus 0. I don't have to write the plus 0 unless you want me to, but I won't. The derivative of x squared is 2x, and the derivative of negative 2x is just negative 2. Derivative of 4 is 0, so it just goes away. And that's it. This is Newtonian, or prime way of writing derivatives. We'll do some more examples in class, ladies and gentlemen, and we'll actually find the slope of tangent lines, which is one of my favorite things to do, because you're going to be doing that all in every section that we do from here. This is section 2.2. You're going to do it in 2.3, 2.4, 2.5, and you might even do it in 2.6. And there's a whole section devoted to what we call Newton's method. And Newton's method helps us to approximate values using the tangent line. We'll talk about that in section 3.9, ladies and gentlemen. Do me a favor. I did sign homework. I will put that in the group chat, and I will also write it in class. Thank you for taking these notes, and we'll see you in class.